Hi, and welcome to this tutorial webinar on overall equipment effectiveness and total productive maintenance. Just to let you know that the slides which I am presenting will be available on Moodle, and feel free to go and have a look at those. And obviously, I'd be more than happy to answer any follow-up questions should there be any. Effectively, what we're going to look at over the next 20 or 30 minutes is the purpose and the main elements of overall equipment effectiveness, how we go about calculating it, talk a little bit about some of the principles of total productive or preventative maintenance. I want to go into the 6 big losses and then talk about preparing and planning to implement the total productive maintenance within your organizations. So let's start out with OEE, and just to clarify exactly what we're talking about and what we mean by it. Essentially, we're combining the availability of the equipment along with its performance during that available time and the quality of the parts that are produced. You can see the little diagram that we have here where we've got the total available time, then we take out the non-planned time and we're left with the green line here, the planned time. Then within that planned running time, we end up with downtime. We could potentially also lose output because the machine is not running as fast as it should be. And of the output that we do get, we may end up with some defective parts in it. So the OEE, or overall equipment effectiveness, is essentially a measure of the availability by the performance, by the quality of the product that's produced. So it measures efficiency of the machine during its planned running time. Planned machine, planned non-running time for the machine shouldn't be included in this calculation. So just to explain that in a little bit more detail, we can calculate it in 2 different ways. There is a very simple method, which is where we look at what we expect to get off the machine or the process over the running time, and then we look at what we actually got out and compare that as a percentage of the expected of the theoretical amount. That gives us an overall level of performance, but it doesn't allow us to get into do any analysis, any meaningful analysis at least, of the specific issues that may have caused those particular problems. So a more detailed method of calculating the OEE is to actually break it out, and we look at the operational availability, which, as you can see here, is the production time over the planned time. We look at the speed factor, which is the actual output over the theoretical output, and we look at quality. So how many of the total parts that we produced were actually conforming to the requirements. Another way of stating that is that the availability is time available for production minus downtime over the time available for production. So we take the downtime away from that, and then we divide it by the time available. Similarly with the speed, it's the ideal cycle time by the number of parts produced over what the actual operating time was. And with the quality, we can look at the total number of parts produced less the defects, and that will give us the divided by the total number of parts, it will give us our percentage of good parts. So each of the 3 pieces are calculated separately. Now, the really nice thing about OEE is that it does allow us to delve down into deeper elements of the machine and of the issues that we might be looking at. So if I look at the operation availability, we can see that this allows us to get into setups, tool changes, maintenance time. It also looks at breakdowns and other things like no material, no operator and such like, which all contribute to the machine not effectively running. Speed factor is the next one, and that in turn can be broken down into physical speed reductions or loss of output, short stops and such like. And also, obviously, the quality rate ties into defects. Interesting point to remember and bear in mind, it's not just the defects that will occur at that process, but potentially defects that are observed later in the product as a result of that process. So the defects can be observed at that point or potentially subsequently. Okay, so what I've got next is a data set, effectively. The intent of this is to allow you folks to actually work through these different sets and test out how effectively you can calculate the OEE value. You'll see here that there's a separate set of data for each day of the week, and it's summarized into the weekly totals. That effectively gives you 6 separate data sets to have a look at. And you can see down the left-hand side, we've got the planned time, we've got information like breaks, changeovers, stoppages, theoretical capacity, and scrap numbers. So effectively, you have all the raw material that you need to be able to calculate what the actual OEE values are. There's a blank form available here as well, and if you download the presentation, you'll have a copy of it. That's to try and make it easier to work through the calculation. So in addition to that blank slide, I also have included a completed section for the first day and for the week, so you can see the summary data. So very quickly, for example, that 840 minutes on day 1, if I move back to the earlier one, there is 14 hours. So 14 hours is 14 by 60 minutes, which gives us our 800. Similarly, the breaks is 1 hour on that, and for the week is 4.5 hours. And if you look on the breaks, where are we? 60 minutes and 270 minutes again. So we've converted them all into minutes, and you can figure out the remaining values are extracted from the chart. And then you can see we calculate the operation availability. We then look at the speed, and then we get the quality. And the OEE value is the product of the three of these. So it's the availability by the speed by the quality. You can see in these particular examples, it's 59. 61. So please feel free to go back over these slides and work through the remaining 4 sets of data to satisfy yourself that you're comfortable enough with the process for calculating this. Answer sheet and that example that we just went through are on Moodle. So as I said, feel free to pull those and play around with them at your leisure. Now moving into preventative maintenance and total productive or total preventive maintenance. Essentially, PM or preventative maintenance involves 3 types of activities. So there's the daily maintenance, checking, lubrication, general inspection that goes on, cleaning down the machines as required. And then there'll be periodic inspections to look at degradation, damage, deterioration, wear and tear, and so on. And then obviously there's the restoration or repair. So that's the kind of daily cycle of preventative maintenance. Total productive maintenance is a step up from that. Preventative maintenance is primarily focused with keeping the machines in good running order, I suppose. But total productive maintenance actually moves into a company-wide initiative, which is not just about the maintenance department or just about the operators. In fact, by and large, the most successful implementations of total productive maintenance programs tend to be led by departments other than maintenance. One of the failure modes, I suppose, is that non-maintenance related departments occasionally, well, more than occasionally, tend to regard this as a maintenance thing. However, the total productive maintenance is actually an organization-wide initiative and does need significant buy-in from other departments to be effective and sustained. It involves employees from all functions and from multiple levels throughout the organization. And really what we're trying to do here now is we're getting 0 breakdowns and 0 defects. So perfect quality, perfect running machine. Again, it's an ideal, not necessarily going to be achieved, but it is the objective. So if we look at TPM, it's an equipment and a process improvement strategy first and foremost. And then if we break it out, it's total because it involves all employees and it aims to eliminate accidents, defects, and breakdowns. So it's trying to create a safe, productive, high quality environment. The productive side of it is where actions are performed while the operation goes on. So we're trying to do some parallel work here. In other words, while the machine is running, the operator may give it a quick clean down. We'll be listening for squeaks, noises, rattles, hums, and so on and so forth. And effectively, by doing that, we're capturing information to enable those machines to keep running and to get in early and fix potential problems where they're allowed to continue unaddressed. The maintenance side is pretty obvious. It's about keeping the machine in good condition. And again, it's back to our preventative maintenance basics, which is about repair, cleaning, and lubricating. And that typically would be taken on by the operators within the area running the machine on a daily basis. Again, worth bearing in mind that this approach is very consistent with empowering the operators, with giving them ownership of their cell, with providing support systems in place. So this is another step in that direction where the process is under the ownership of the operators, and we're tooling and skilling them up to be able to interact more effectively with the equipment and to collaborate more meaningfully with the maintenance crews. Okay, so that's essentially what our TPM is. The key goals, obviously enough, to maximize the effective utilization of the assets that we have, the equipment that we're running. We want to meet our production schedules, not get unexpected stoppages and disruption to the operation. Obviously, we want to keep the machines running for as long as we possibly can. And in fact, there is an interesting perspective that when the TPM program is effectively implemented, that equipment will actually improve with age. Maybe like a good wine. But essentially, that with the ongoing TPM work that will be done, the capacity and the capability of the machines could potentially be increased over time, and at a minimum, certainly show no deterioration. Fully supports the overall plant or facility mission, which is to get the product made. And it looks at process flow, it looks at takt time, standardized pull, Judoka. So it synchronizes in with a lot of the other lean activities that will be going on. As I mentioned earlier, the operator empowerment being one of those two. There are 5 key principles that underline, I should say, TPM. So first and foremost, it's maximizing equipment effectiveness to try and improve productivity. Secondly, is to put a PM system in place that focuses on the entire equipment life. Key piece of TPM. Coordinating all of departments, including those that design, maintain, and operate the equipment. So this is the big step beyond the traditional PM environment where it's just the maintenance crew. This is about people who are specifying the requirements, designing the machinery, and running the equipment. So it's a full lifetime engagement, if you like, or engagement of people who are involved with the machine throughout its life. And vertically through the organization, the same is true, not just the shop floor operators, but up and down the organization as well. Obviously, it's team-based activities, as are so many other things in the lean space. Value stream mapping, Kaizen, TPM falls in there as well. Now, there are 5 pillars, and these drive the types of actions and activities, I suppose, that go into sustaining a TPM environment. And these are all important elements that need to be managed. So the first one is improving activities to increase the effectiveness of the equipment. Then we look at autonomous maintenance by the operators. A planned maintenance system needs to be put in place. There typically will be significant training required for operations and maintenance staff to upgrade their skills to the necessary level. And also the equipment design going forward. We want to try and design in to future equipment features that will reduce the amount of maintenance work, that will enhance the performance of the machine and such like. So let's go into each of these 5 in a little bit more detail. Equipment and process improvement. That really brings us into the 6 big losses, which I mentioned at the start of the tutorial. So these basically are categorized as breakdown losses, fairly obvious. Speed losses, where machine running slower. Setup losses, we all know about the time it takes to set up machines. Defect losses, pretty self-explanatory. Startup losses, so very often when machines do get set up, they start running at a lower speed for a bedding in period of time. And also a minor stoppage losses, one of the interesting ones I'd suggest, because in many organizations, these are not even recorded. So it's the machine stops for 30 seconds, there's a bit of flash stuck in a press or a bit of swarf that's got in the slideway, has to be cleaned off, and then the machine starts cycling again. Often these are not recorded and unnoticed. However, they do actually occur quite frequently during the day. When we get into analyzing these 6 big losses, typically that's one that accounts for a surprisingly large amount of the actual stoppage time. There's a lot more information on these 6 big losses within your workbooks, the course material, so I would encourage you to go and look a little bit more deeply into those. In addition to those 6 big losses, there are a number of other areas that can be identified when we go through the OEE process in using TPM. So in addition to the 6 big losses that I've got identified here on the left-hand side, we have manpower losses, so cleaning, checking, waiting for materials, instructions, waiting quality confirmation, all these types of things that go on pretty much on a daily basis in many organizations. Plus you've got material losses, quality defects that are not related to the equipment process itself, material defects, and so on. So we have lots of opportunities in terms of, as I mentioned, improving and increasing equipment effectiveness. So moving into autonomous maintenance. Sorry, before I move into the autonomous maintenance, another key issue, obviously, to bear in mind in terms of process and equipment improvement is the process quality management. So are we recording data? Are we measuring performance? Are we reacting to all of that? So again, that's an area that should be looked at in terms of the improvement space. Longer term, you may look at issues relating to deterioration from neglect, quality of maintenance might not be up to scratch, getting into analyzing root causes before repairs are done, just a list of some of the various things that often pop up as we get further and further into maintenance programs. So autonomous maintenance is where the actual product builders or the equipment operators become involved in and take primary ownership for the maintenance of their own equipment. And there's three basic objectives that have to be satisfied when we do that. The first one is that operators and maintenance are collaborating together to stop the machines from degrading and to deal on a daily basis with ongoing issues. Another key one is to help operators to better understand how their equipment functions, so that if we're getting them more responsible for the total preventative maintenance, one of the key things we need to do is we need to skill them up and tool them up in terms of understanding how the machine operates, how problems can occur, how they can be avoided, and that. So there's quite a lot of development and training work is needed as part of that autonomous maintenance. And thirdly, we're trying to empower the operators to try and partner with maintenance and engineering to try and improve equipment performance and reliability. So it's a significant step up in terms of what we're looking for our product builders to do, certainly if you consider it in comparison to a more traditional industry. So effectively, we're trying to train to close the gap between the operators and the maintenance staff, better team working and a seamless ownership in terms of resolving issues on the machine. We also want to try and change the equipment so abnormal conditions can be easily identified and that we can measure deterioration before it affects the process or leads to failures. So we're trying to get in before we have catastrophic failure, before components or parts are getting damaged. A simple example of this, one of the years when I worked in a foundry operation, we had operators who stopped a line one morning because one of the press operators noticed that there was a whine on the pulley at the top of the press that hadn't been there yesterday. We went in on a break and we did a quick inspection and discovered right up the top of the press, we discovered that one of the major belts that drives the press was beginning to come apart. There were a couple of clips that were holding it and, a couple of the clips that were holding it had come loose. And effectively we planned a maintenance intervention that evening. Had we not heard the noise and made that intervention, the belt would have snapped ultimately, and we would probably have had if not catastrophic, then certainly a failure that would have resulted in a lot of damaged components, plus an awful lot of lost production time. So within this autonomous maintenance space, there are 7 fundamental steps that are implemented in sequence, which increases over time the operator's knowledge, their participation, and their responsibility for their equipment. So here we have a quick summary of the steps that are involved and the various activities that relate to those steps. So if we just have a look here at the different steps that are involved. So initial cleaning, pretty straightforward. Eliminating inaccessible areas and sources of contamination. So that's about modifying the equipment and making sure you can get access into it. Developing cleaning and lubrication standards. General inspection skills training. Then we get into them conducting their autonomous inspections, followed by visual maintenance management, and ultimately performing ongoing maintenance and improvement activities. So they're the 7 levels, if you will, in terms of progressing through the autonomous maintenance sequence. And then there's a summary of the types of activities that would be associated with each of those steps. The next slide actually covers the goals for each of those steps. So on the previous one, we talked about the specific activities, and here's why those activities are being done and what we look to get out of them. So for example, if we move down to conducting autonomous inspections, the operator goal is to learn the importance of data recording, to be able to learn proper operating methods, and to be able to detect signs of abnormality and develop appropriate corrective actions. So again, operator goals for each of the steps and the specific activities that are aligned to them. Autonomous maintenance was the second item we mentioned, along with equipment improvement. The other one is plant maintenance. So it's important to establish a preventative and a predictive maintenance system for equipment and tooling going forward, looking at the full life cycle of the machines and looking at all those different areas, lubrication, retightening, spares, so on and so forth. So there's a lot of work in the basic planning work that needs to go on. Also, I mentioned education and training, and that's the fourth of the 5 key pillars. And it's 2 major components. It's the technical aspects, obviously enough, in terms of enabling operators to understand what they have to do, but it's also the soft skills training, building team working, diversity, communication, and such like, to try and get a more collaborative and engaged workforce at all the different levels that are involved. Okay, and the final one is early management of new equipment, if you will. So how do we shorten startup commissioning and stabilization time for quality and efficiency? If we're designing or bringing in new products or equipment, how engaged are we with the manufacturers, and how specific are we in terms of our requirements around the maintenance area, not just the operational side? So we ought to be thinking about operating, cleaning, maintaining, access, and all of these other things. So they're basically the 5 pillars. And then I just briefly want to summarize with an overview of how we implement it. So again, you'll see on this slide, there's a significant amount of preparation activity. So there's announcements, there's education campaign, there's promotion activity, getting a committee organized, basic policies and goals have to be developed, and then the plan itself to actually implement it. So there's quite a lot of planning and preparation work involved before you ever get into the actual kickoff of it. And then through the implementation, you can see there's a whole series of steps and activities that are required as well. So it's a long-term undertaking. It doesn't happen quickly. It does yield very significant benefits, and it's a key piece in terms of enabling your lean operation to run the way you expect it to, with uptime and reliability, plus engaging your operators and deepening their sense of ownership and control over the processes that they're responsible for. Okay, so that concludes my presentation on OEE and TPM. I hope you found it interesting. And as I mentioned earlier, the slides are available on Moodle. And if you have any questions or queries, please get back to me. Thank you very much for listening, and take care.